Right, so in this video we're gonna look into increasing functions and decreasing functions. So what criteria must be met to determine whether the function increases or decreases? So this will be looked into in this video. So how can we say if a function whether a function increases? First of all, we have to specify a domain, right? A region of x values, otherwise it will not make any sense. So as you have seen in the introductory video, we had parabolic functions. So we can't say the function increases there, right, in general, because function decreases up to a certain x value, then beyond that x value function increases. So we have to make sure the domain for, right? So suppose on an interval of x values between a and b, including a and b, you can see square brackets, that means a and b are included. If for each pair of x1 and x2 within that interval, suppose we have an interval like this, this would be our x-axis, a and b. So function is defined in this direction, in this region. So if we choose any x1 x2 pairs, if you choose any x1 x2 pairs where x1 is less than x2, so x1 is closer to a than x2, then if this is implied, f of x1, that means the y coordinate of the function at this point is less than the y coordinate of this function of the function at this point, then we say the function increases on this interval. So let me show you what it means using a graph. Okay, right. So on an interval from a to b, right, so a function can increase in two different ways. So the shape of the curve is different in these two ways. So we will learn how to distinguish between these two shapes later on this course, but for now you should know that function can increase in this manner or in this manner, right? So if we select two pairs of x1 and x2 such that, suppose our x1 was here and then our x2 here, like this would be our x1 and this would be our x2. You can see the coordinates, right? Y coordinate, the function here is less than the value of the function here. Same thing, you can see this would be the value of the function at this point, and the value of the function at this point would be this. Obviously this point is greater than this point, so let me write f of x2, this is f of x1, this is f of x1, and this would be f of x2. So this is how we can say whether the function increases or decreases. So this is the definition, but how can we use it? So we're gonna come up with two pairs of x values, then substitute that x value into the function and get an output and check whether these two numbers are different or not. So that's not the right way to go, because it would be quite arduous. So there's another method to tackle this problem and test whether the function increases or decreases. Now here's the thing, so let me just erase this for a moment. Right. So what happens is that, if you can see, what is the meaning of differential coefficient? Differential coefficient means, suppose this is our y equals f of x, then what does f dash of x represent? F dash of x represents the gradient of the tangent line, at any given point on the function. Suppose we are here, then this would be the tangent line drawn to it, right? So it increases indefinitely. I'm not going to do it. If you are here, this would be the tangent line. Here, this would be the tangent line. Same way here, tangent line, again tangent line, right? Sorry about that. Right. Now if we look at this, what can we gather from this? The tangent line. So what can we say about the gradient of the tangent line? The gradient will be always positive. So if the function increases, you can see the gradient, see, it makes an acute angle with respect to the positive x-axis. So our gradient, also known as the differential coefficient or the derivative of the function, is positive, right? So we know that. So we can check for this. Instead of going to this one, we can just check the derivative of the function and check the sign of the function. So from a to b, the sign of f dash of x is positive always. So this is how we check it. F dash of x is positive. Implies both ways f of x, or we can call it y coordinate, increases. It implies both ways. What does that mean? If function increases on a certain interval, on a region, then we can infer that the derivative of that function on that region is positive, right? So this is implied both ways. Now this is a graphical representation. Now this would be the gradient would be f dash of x, the gradient, okay? The gradient of the tangent line would be f dash of x, not f of x, f dash of x. So you can see the prime here, okay? So let me use another color, prime, okay. So clearly mention this. Now you can't just take my word for that. Let me prove it. We have to prove this. So whether we can use this fact to check whether the function is increasing or decreasing. So let me write down the proof here. So I will do the proof for this one. Then for decreasing functions, I will not do the proof. You guys can do the proof by yourself. So this is how you prove it. Now I'm going to take two values. So let me take this to be my x and this point. Now since derivatives are involved, I'm going to take x and a small change in x value. So let me just call it x plus delta x. So the function at this point would be f of x, and the function at this point would be f x plus delta x. So since delta x is positive, it's a positive quantity, definitely x plus delta x is on this side. So this is true, this is satisfied. So what does that mean? As you can see, fx plus delta x is greater than fx. It's not equal, it is greater. So let me take it to the other side. X plus delta x minus f of x must be greater than 0. Now what I'm going to do, I'm going to divide this whole thing, whole inequality, by delta x. So since delta x is a positive quantity, the inequality will not change its directions. Right. So let me write it down again. And fx plus delta x minus f of x divided by delta x. So what do you get when you divide 0 by any quantity? It is 0. So let me write 0. Now what I'm going to do is I'm going to take the limit on both sides as delta x tends to 0, because to get a good idea we need to have these 2 points closer together, very close to each other. So that's why we are using limits here, and we should incorporate limit on this side as well, even though we don't have any delta x terms there. And what does this mean? This is the definition of differential coefficient. So this is defined, this whole thing is defined as f dash of x. If you can't remember this, please go through the notes. So you can see this. So what does that imply? That means if the function is increasing, f dash of x, the derivative of the function must be positive. Or if the derivative of the function is positive, that implies the function is increasing on that interval. Right. So what's the sign? So let me just summarize it here. Right. For an increasing function, the sign of f dash of x is positive. You can see it is positive. And the visual representation. So visual representation is very important. This is what we want before we start sketching curves, right? So we're gonna use directed line segments, so small line segments to guess the shape. So what does it mean? I mean, what type of line segment will represent a positive gradient? So that would be a small line like this, small line, which is inclined to the positive x-axis by an acute angle. So this would be this is also called directed line segment. So keep in mind. So if we have this directed line segment that looks like this, small inclined lines, so that means the derivative is positive in that direction. Okay. So let's move on to decreasing functions of x now. Right. So decreasing functions, fx is said to decrease on an interval ab containing both a and b if for each pair of x1, x2, if you select two pairs of x coordinates such that x1 is less than x2 on the interval, if f of x1, that means the function at this point, is greater than the function at this point, then we call them decreasing functions. So suppose you are here, if this is x1 and this is x2, you can see the function, the decreases. What is meant by the function? That means the y coordinate. If you are here, the y coordinate here. If you are here, the y coordinate here. So the function decreases. This is just to illustrate on this. So we don't need this one. Now what happens? So we don't need to use this definition or definition as a test for this. So we can just use the derivative of this function. You can see the small tangent lines here. These are called directed line segments. So they make an obtuse angle with respect to x-axis, right? All of them. So it can decrease in this direction, in this way, or in this way. In both ways, function can decrease. So you know that then if the function decreases, the derivative must give you a negative value. So this implies both ways. If the derivative is negative, the function or the y coordinate decreases, or if y coordinate or the function decreases, the derivative must be negative in that region, right? So the summary, sign of f dash of x would be negative, right? If you get negative, then what does that mean? It means the function is decreasing on that interval. So what about the visual representation? So you can see these small directed lines. So this would be the visual representation. So I'm not going to do the proof for this one. You can do the proof by yourself. Next, we'll look into some example and figure out this intervals of x values where the function increases or decreases. Right, so we'll start with a simple example. This is a quadratic function. You can see the coefficient of x squared is +1, which means it would give you a minimum, right? So this is how you go about obtaining this result. So determine the interval of x values for which the function decreases or increases. So how determine? To determine whether a function increases or decreases, we need the derivative of this function. Sometimes the question will say f of x equal x squared plus 3x plus 2. It's the same thing. It's the same thing. So what we do is we take the derivative dy by dx. So derivative of polynomials. This becomes 2x, this becomes 3, and this becomes 0. Now this is what you're going to do. You're going to find x values for which the derivative becomes 0, because we need to know the regions where the sign of the derivative is positive and negative, not 0, right? So first we need these critical values, so we call them critical values, and in future we'll call them turning points, right? So keep that in mind. So first of all we need to find for which x values that this derivative is 0. Then we use a number line to represent it. We use a number line, okay? Number line, just like we did with inequalities. Then you represent the x value for which derivative is 0 here. So what is the x value for which this derivative is 0? If we put minus 3 by 2, this would be 0. So the value is minus 3 by 2. This is the value. Okay. Then you look for the sign of f dash of x. Sign of f dash of x. So you represent sign of f dash of x here. Now this is a special point, and our regions are separated by this point. So if we have maybe 2 factors here, then you have to look for both x values for which dy by dx is 0. Now in this case we have a linear factor, so there's only one, which splits our x values into 2 different regions. So the first region is when x is less than this value, the second region is when x is greater than this value. So what happens to the sign? So all you have to do is you can do the working here below this line, just like we did with inequalities. Now minus 3 by 2. So if you want to know what happens in this region, you just come up with a number which is less than minus 3 by 2 and substitute it here. Substitute for x and check the sign. So minus 3 by 2, anything less than that, let's say minus 2. Minus 2 is less than this. So that gives me minus 2 times 2 minus 4. Minus 4 plus 3 is minus. Right. Sometimes if you have 2 factors, then you need to work it out here. So our result would be negative. Right? Negative. So around here, anything greater than minus 3 by 2, the base number is 0. If we put 0 here, this would be positive. So our sign of this one will be positive. Right. So once you figure this out, you have to summarize the result. Now what happens? Sign of f dash of x is negative. Right? When you are below minus 3 by 2, sign is negative. What does that mean? It means the function is decreasing. Function is decreasing. So it could be like this, right? Or like this. When you are more than minus, when x is greater than minus 3 by 2, the sign is positive. Positive implies the function is increasing. So it can increase in this manner or this manner. We still don't know. We are still figuring things out. So don't rush into this one, because this is very important. There will be a complete question based on these things, right? Based on this one and the next type of application, the practical applications. Then we have to summarize this result. So we use a table to summarize this one. So draw the table below this. Since I don't have, I do have space, but it's better to draw it now. Or maybe just do it here. It's fine. Then we can summarize this in a table. So on this side, first one is the interval to represent all the x values. then sine of f dash of x, then nature of the function, whether it increases or decreases. Now since we have two regions, so we just split it into two. Include this one, we have three columns. Now mention the interval. Now our x, if we are in this region, that means x is less than minus 3 by 2. If we are on this region, our x would be greater than minus 3 by 2. Sign, look for this. This is negative and this is positive. Negative means decreasing. Positive means increasing. Right. So let's look at another example. Right. So next we have this function y equals 2x cubed minus 6x plus 5. So you don't know about these functions, how to draw them especially. These are called cubic polynomials. So let's see. First you need to check where the regions or the intervals of x values for which the function increases or decreases. For that you need the derivative, so derive this function. Easy, 3 comes to the front and multiplies by 2, so that is 6x, and 1 will be deducted from 3, these are with 2. Then minus 6 and the constant becomes 0. So then we have to do some working. We have 6 is in common, so that gives us x squared minus 1. So what else can we do with this? You can see this is difference of 2 squares, so 6 into x minus 1, x plus 1. So notice here, this coefficient, if it is a positive coefficient, then we don't really have to care about this one. If it is a negative coefficients, then we have to take that into account as well. Okay, so now let's look for the x values for which the derivative becomes 0. So when you apply x equal 1, the derivative becomes 0. X equal minus 1, again derivative will be 0. So there are 2 points, minus 1 and plus 1. Circle them because these are included. These x values are included there. So what happens at x equal minus 1, derivative will be 0. At x equal plus 1, derivative will be 0 again. Now we have to check for the sign. So put 2 brackets there, empty brackets. Then a number less than minus 1 in this region. Then let me take minus 2. If you take minus 2, this is minus 3 and this is minus 1. So both minus, which means positive. Then a value in this interval. So the base number is 0. If you put 0 here, this is negative. If you put 0 here, this is positive. So this would be negative. Greater than 1, let's take 2. X equal to, this is plus. X equal to, this is plus. Right. So now you can see, if you are below minus 1, the sign of f dash of x is positive. What does that mean? The function is increasing. If you are in between minus 1 and plus 1, derivative is negative. That implies the function is decreasing. It could be like this or like this. Then greater than 1, the function is increasing. So now these two values split our x values into 3 different intervals. This is first, this is second, this is third. So first interval is less than minus 1. So x is less than minus 1. So let me put minus infinity as well. I forgot to mention this one in the previous one, right? Because it's obvious, but write that down. Then the other interval is between these two values. Then x is greater. මේ පැත්තේ එකට මේ පැත්තේ එක මේ පැත්තේ ඉන්නවා. Sign positive, negative, then positive. If it is positive, it means increasing. If it is negative, means decreasing. So this is increasing. Right. So we'll look into more of these types of questions during the online session. Right. So I discussed 2 examples. So we'll discuss more examples in the class. And now let's in the next video we'll see how to find turning points or station points. So stay with me on this.